Okay, welcome everybody. So if you haven't watched the first circuits video introducing the topics of circuits, types of circuits, and parallel and series resistors, you should go and watch that first, because this is an example of a very complicated, or at least the most complicated type of circuits problem that you're likely to see on the AP exam. So I'm going to walk you through this one. If you, at the end of the last video, decided to try it, you can follow along with your solution and see if you're going about it the right way and if we come to the same answer. If you haven't, if you want to pause this right now and give it a shot, be my guest. However, I'm going to jump right into it right now. So the most important thing that we need to keep in mind is only one law really that matters, and that is Ohm's law. Ohm's law being voltage is current multiplied by the resistance. So that means the total voltage of a circuit is equal to the total current multiplied by the total resistance. This can also apply for individual circuit elements. So what we need to do first is the strategy that we need. We have to list what we have. We have the total voltage is 40 volts, as we can see right there. Right. Our total current is unknown, and our total resistance is currently unknown. We can see that we have a whole bunch of different types of resistor combinations. We have, this is one set of series, and then these are all in parallel, and then these are in series. So what we're going to do is we are going to attempt to break this circuit down into the most simple circuit. We want this right here. We want this. We want a very simple circuit where we have one source of EMF and we have one equivalent resistor. Once we have that, then we can find the total current, and then we can work from there. So let's give that a shot. Let's start with these. So let's find the equivalent resistance of those two circuit elements. So what we want to do is we want to end up with a circuit that looks like that. So that means that we are going to be putting together R2 and R3 into this resistor, and we are going to be combining 4 and 5 into this resistor, okay? So that's what we're going to do. So we are going to call this R23, and this is going to be R45. See if I can't even read that. 2, 3, and R45. So since these are in series, R23 is going to be R2 plus R3. And so that means R23 is 10 ohms plus 30 ohms, which is 40 ohms. And R45 is R4 plus R5, which is 15 plus 20, which is 35 ohms. Okay, so now we have R23 is 40 ohms, and R45 is 35 ohms. Great. So now we have that. Now let's break this down into an even simpler circuit. Let's say we want this circuit right here. Okay, so what are we doing here? Well, we are taking resistor 2, 3, and resistor 4, 5, and we are combining them into this equivalent resistor. So we are saying that these two, which are already equivalent resistors, are now going to be made into a third equivalent resistor. And we're going to take these two that are in parallel, and we are going to figure that out. So we are going to call this R2, 3, 4, 5, and I know my writing is terrible. 2, 3, 4, 5. There we go. So that means what we need to do is we need to see that R2, 3 and R4, 5 are in parallel. How do we find resistors in parallel? So we use the inverse of the equivalent resistor. R2, 3, 4, 5 is equal to 1 over R2, 3 plus 1 over R4, 5. Okay, that means we're going to have 1 over let's see, 40, my apologies, plus 1 over 35. All right, so 1 over 40 plus 1 over 35. Great. Now we need to grab our handy dandy calculator and figure out what the least common denominator is. Let's see, we could do real simple. Why don't we just do the simplest one, and we can say that this is 35 over 1400 plus 40 over 1400. And that is 75 over 1400. Running out of space. So what have we found? We have found that we have 1 over R2, 3, 4, 5 is equal to 75 over 1400, which means if we take the inverse of both of those, that means R2, 3, 4, 5 is equal to 18.66 bar ohms. And let's just do a quick sanity check. So we have R2, 3 and R4, 5. Okay, and we have 40 and 35. If they are in parallel, that means that the equivalent resistance should be lower than each of them individually, which it is. So we are all set on that front. So that means we now have a very simple circuit right here, and that is R2, 3, 4, 5, and from way back, R1 is right there. So I'll redraw that a little larger, so we can get that R1. Great. Now we want to simplify that to the simplest possible circuit. That is going to be, my bad, one source of EMF and one resistor. This is going to be our total. This is going to be our total resistor. And what do we have? We have R1 and R2, 3, 4, 5. Those are in series, right? We see that we can go from one directly to the other. So that means our R total is R1 plus R2, 3, 4, 5. And that is 25 ohms plus 18.6 bar, which equals, never trust me to do arithmetic, 43.6 bar ohms. So that means we have a total voltage, total EMF of 40 volts, and a R total of 43 0.6 bar. Hello, come on. Ohms. Okay, so now we can use Ohm's law. The total is the total current multiplied by the total resistance. So we have 40 volts equals total current times 43.6. And that means that the total current through the circuit is, come on calculator, approximately 0.916 amps. Okay, so we have our major information here, here, and here. Okay, so we've got our total circuit elements, and now we can figure out some other stuff. So what do we want? We want the voltage and current across each resistor, and then the power. And once we know the voltage and the current, it is ridiculously simple to find the power. We literally just multiply voltage and current together. So what are we going to do? We are going to say, okay, R1. Actually, let's make a table here. So we have R1, R2, R3. Help us keep our heads straight. R5. All right. Drawing lines, drawing lines. All right, super. We want 3 columns for now. So we're going to say resistance, current, and voltage. Okay, so we know the resistances. So R1 is 25 ohms. Let's go back. R2 is 10, R3 is 30. R4 is 15. And R5 is 20. Okay. So for R, we know that let's start with R1. Let's start with R1. We know that R1 is in series with R2, 3, 4, 5, and that those two combined, a different color here, those two combined make the total. So R1 is in series with R2, 3, 4, 5, which means that R1 and R2, 3, 4, 5 each receive the same current because they are in series. Series resistors receive the same current. So that means that R1 receives 0.916 amps of current. And if we quickly want to do V equals I times R, we can find that the voltage is 22.9. So the potential difference, the voltage drop caused by R1 is 22.9 volts. And we're going to erase that since we don't need that anymore. What are we going to do next? Well, we know that R2, 3, 4, 5 is, where is it? 18.6 bar ohms. And now we know that R2, 3, 4, 5 receives, we can call this I2, 3, 4, 5. Since it is in series with R1, R2, 3, 4, 5 receives the same current. Therefore, R2, 3, 4, 5 receives 0.916 amps of current, and therefore the voltage that it receives, we have V equals I times R. So we have 18.6 bar times 0.916. We have that those voltages are 17.098, and we're gonna do ourselves a favor and round up. Okay. Volts. All right, and sanity check. So sanity check. We know that Kirchhoff's voltage rule says that the sum of all the potential differences across a circuit must equal 0. That means that we have a total of 40 volts that must equal V1 plus V2, 3, 4, 5. Since we have a voltage drop across R1 and we have a voltage drop across R2, 3, 4, 5. That means we have 17.1 plus 22.9, and that gives us 17.1. I'm doing this in my calculator because arithmetic, but we do indeed get 40 volts. So sanity check. We're good, right? We have dropped the correct amount of voltage across the entire circuit. So sanity check, we're all set with that. Great. Moving on. So now we're basically going to go backwards. We know that R2345 was made up of R23 and R45. If we look way back up here, right, we saw that 2345 was parallel R23 and R45. Great. That means that R23 and R45, since they are in parallel, they receive the same voltage. So that means that R23 is, if I can find it, there it is, 40 ohms. I'm going to make a line right here so I don't get lost there. All right, R23 is 40 ohms, and that means that the voltage 23 we get is 17.1 volts. And similarly, R45 we got as 35 ohms, and voltage across 4 or 5 must be equal 17.1 volts. Okay, so at this point, what we've got is we have worked backwards, basically, from the simplest possible circuit to the next simplest to the next simplest, and then eventually we're going to make it back to the original one, right? But right now, we're working with R23 and R45. We're almost there. We're almost there. So now we know that R23 and R45, they have to have the same voltage, the same potential drop across them. That means we can use Ohm's law to find the current through each of these. I will do that quickly. That is going to be the voltage divided by the resistance. So this is 0.4275 amps. And this is 0.48857 some odd amps. Okay. And then, as always, we can do a sanity check. Kirchhoff's loop rule says that we have to have the same amount of current going into and coming out of a junction. That means that these two right here added together should equal this little guy over here. And if we do that, that means we get okay, yeah, plus 0.4275 0.75. Yep, indeed we get 0.916 something something something. So we're close, right? Because I had to truncate my decimal somewhere in there. All right, so we're good. Sanity check. Hooray, sanity check. We're good. Okay, that is an 8. That is an 8. Okay. So we're getting there. We're getting there. So we still have some stuff to put into this table. However, we can actually fill in some things. So let's scoot back a few frames here and remember that R23 is R2 and R3 in series. Series means that those resistors receive the same current. Same with R45 is R4 plus R5 in series. So that means that R2 and R3 are going to receive the same current as R23. So that means that R2 and R3 each receive 0.4275 amps. And then since 4 and 5 are connected to 4 or 5 in series, that means they receive the same current, which means that 4 and 5 receive, we're going to truncate it a little bit earlier, 4.886. Okay. And there you have it. There you have it. Could not be simpler. Could not be simpler. So now we're going to use a final. Voltage is current times resistance, and we can find the potential drop across each of these. So we're just going to multiply across 10 times 0.4275. 4, oh, that's in blue. Oh no, my chart. 4.275. 30 times 0.4275. 12.825. 15 times 0.4886. 7.329. And 20 times 0.69.772. Great. So, final sanity check. Final sanity check. We have 5 circuit elements. The potential drop across all of these circuit elements should be 40 volts. Let's add them all together. Plus 7, so 9.772 plus 7.329 plus 12.825 plus 4.275 plus 22.9 equals a whole bunch. Oh, what did we do wrong here? Try that one more time. 9.772 plus 7.329 plus 12.825 plus 4. Well, I think I missed. No, I don't think I. No, I didn't mess up anywhere. Well, regardless. All right, I'm gonna have to pause this and then maybe add a explanation of what may have gone wrong in a comment. Yeah, that might be what I have to do. Anyways, let's find the power. Let's find the power in each of these. Power is current times voltage. All right, so we very simply can multiply across. Very, very simple. So we have 0.916 times 22.9. This is 20.97 watts. And we have 0.4275 times 4.275, 1.827 watts, 0.4275 times 12.825 equals 5.482 blah 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 watts. 0.4886 times 7.329, 3.5809 watts, and finally 0.4886 times 9.772 is 4.7746-ish watts. Okay, so we found the power. And I'm going to end this here, and then I'm going to do a sanity check of my own, and I will either put it in the comments or I will tack it on at the end of this video. Thanks for watching.